at Naval Postgraduate School in 1994. So he's been a key contributor to US Arctic research for a long time. And I would say his largest contribution has been in understanding high resolution ocean simulations and coupled regional simulations of the Arctic. So he was renowned early on in the mid or early 2000s for producing the highest resolution ocean simulations of the Arctic, fully Eddy-Resolving down to 9 kilometers and then pushing the boundaries down to 2 kilometers resolution, or 2.5. Since that time, he has gone on to many other great things, including seasonal prediction of the Arctic using the regional Arctic system model. And today he'll be talking about a number of things, including AEROSI, which is a new project using E3SM, predominantly in G cases, to simulate the Arctic again at high resolution using EMPAS Ocean. There are several contributors to this project within E3SM, but I'll let Wieslaw introduce them and introduce his project. And I'd like to thank you, Wieslaw, for giving this talk.
Thank you, Andrew. Thank you, Wuying, and the organizers to get me on this webinar. Really appreciate it. First time doing this presentation at this forum. And I would like to talk about the E3SM AEROSI project. So the AEROSI project stands for Arctic Refined Eddy-Resolving Ocean and Sea Ice Model. And the whole idea here is that we are addressing the common limitation in global ocean models and sea ice models, where the Arctic is typically under-resolving eddies. The 3 kilometers in the Arctic, based on the radius of deformation, it's predominantly sufficient to represent eddies in the deep basin. Probably we are still underrepresenting on the shelves, which are a significant portion of the Arctic region. This project, E3SM AEROSI, basically looks to explore the benefits and demonstrate the gains of the E3SM core capability, being the regional refinements and high resolution. And the other kind of like longer term objective for this project is just to prepare for Exascale and coupling E3SM components at a very high resolution model. My team consists basically of 2 institutions, the Naval Postgraduate School, where I'm from, including Youngju Lee and Jacqueline Clement-Kinney, and the colleagues from Los Alamos National Laboratory, Mark Peterson, Andrew Roberts, and Milena Veneziani. We also have on the team a non-funded by DOE, a long-term collaborator, Robert Osinski from the Polish Academy of Sciences, Institute of Oceanology. So just a brief outline. I'll give you a one slide project summary, discuss a few things about the model configuration and simulations, and then show a number of intercomparison of several G cases, V3 G cases with different model configurations that are currently standard configuration on the E3SM options. I'll start with the intercomparison of AMOC simulations, the upper ocean circulation, vorticity of Kubo ice parameter, sea ice thickness distribution, volume time series, gateway transport, surface turbulent fluxes, and summary. I hope I can cover this all together in the next 20 minutes or so. The project, just a one-page summary, is basically to configure a new grid for the E3SM, EMPAS Ocean and Sea Ice, where we are addressing limitation in the Arctic in terms of requirement for high resolution. And this E3SM AEROSI model objectives are to investigate impacts of Arctic Ocean mesoscale dynamics on the northward mass and property transport into the Arctic Ocean, shelf basin exchanges, and impacts on the upper ocean and sea ice within the Pan-Arctic region, air-sea exchange momentum and heat within the Pan-Arctic region, and then export of fresh water and potential impact on the Atlantic meridional overturning circulation. So here's a slide showing the AEROSI grid distribution, which is basically a high resolution V3 in the southern hemisphere. And let me show, switch here to laser pointer. The southern hemisphere is basically 18:6 V3 grid, and we modified the northern hemisphere to address the issue of high resolution requirements in the high latitudes. So basically, the light cyan color here represents 3 kilometers or less over the region as it's shaded. We also iterated the grid in the northern hemisphere to represent the western and eastern boundary currents. Go with the high resolution into Mediterraneans and the Gulf of Mexico or Gulf of America and so forth. The little insert on the left is representing 3 other model configurations that I'll show some intercomparisons with. The 60-30 is the V2 coarse resolution standard configuration. The red line represents 60-10, which is the complementary project by the RGMA EDY-RASM, where we increase resolution to 10 kilometers in the northern high latitudes. And also we have a few comparisons with the standard low resolution V3 at roughly 30 kilometers. So again, as I said, the northern hemisphere goes up to 30 kilometers less, increasing to 18 kilometers subtropics. And basically, those results I'm presenting here are from the first loop of 63 years GK simulations, first with JRI-55, which we completed about 2 months ago. So this is just work in progress. And we have also completed the complementary simulations with V3, 60-10, 60-30, and 30. So first results I'd like to start with is the AMOC simulation. The middle panel is showing time series of AMOC at rapid array latitude 26.5. And there's 4 different simulations starting from no motion. So that's the early part of the spin up. And the blue line is the 60-30 configuration. The red line is 60-10. The cyan is 30 kilometer newer version of the coarse resolution. And then AEROSI, it's shown in a black line. The little numbers on the right show the 63-year mean. So you can clearly see that we continuously improve with the high resolution from 10.5 Sverdrup for the 60-30, all the way to 15.5 Sverdrup for the AEROSI, which is still not as much as we wish to have, but I will address that issue with in a few slides. The inserts on the left and right are basically the stream faction in the North Atlantic, showing the overturning circulation, and the color shading represents the maximum overturning circulation magnitude. So we go about 15 Sverdrup in the AEROSI configuration. The next one is the 30 equal V3, roughly about 12.5 Sverdrup. You can clearly see how the coarser resolution decreases the magnitude of the overturning. And the other thing is that if you look at the end of these 63 simulations, those means are actually higher than the end of 63 simulations, which is why we believe we need to run at least a second cycle of JRI-55 to understand how the model stabilizes with the atmospheric reanalysis forcing in the fully 63-year cycle without the spin-up. So here we're showing the comparison of the overturning circulation to other stream function estimates, including the ones from a paper by Jackson et al. 2019, where they intercompare a number of ocean reanalysis, such as GLORIS, GLOSI, ORAS, GECKO, and a number of other ones. The upper right panel represents the overturning maximum stream function at 26.5. And I'm repeating the 4 configuration with the G-case E3SM V3 on the left with a different scale. You can see that comparing the structure of the overturning circulation looks very reasonable, especially for the AEROSI in terms of the magnitudes. And if you go back to the panel here, about 1,000 meter depth, most of the models are showing somewhere about 15 to maybe 17 Sverdrup. There's one outlier, the North CPM, showing up to 30. So it's not only underestimation, but also it could be overestimation. One interesting thing that we also did with the V3 simulations, we managed to complete the fully coupled B case simulations of the same version like we're showing the G case, so 60 to 10 and 60 to 30. When we run 60 to 10 fully coupled, we go from about 11.8 sphere with AMOG, about 2.2 sphere higher, roughly 14 sphere in the historical simulations. But this is not the version 3, this is version 2.1. We have not completed version 3. We have a 60 to 30 also increasing from 10.5 sphere in the G case, and B case is increasing the strength of the AMOC by about 2.5 sphere to about 13. So the message I'm trying to communicate here is that we expect that if we go with the E3SM AEROSI configuration to a fully coupled B case, we may expect that from 15.5 sphere currently, we can go another 2.5 sphere more. So we'll be roughly about 18.5 sphere for the AEROSI. That's at least expectation for the B case. And also on the on the right panel, I'm showing that reanalysis, ocean reanalysis compared to rapid observations are commonly underestimating the strength of the AMOG by roughly about 1.5 to 2.5 sphere groups, like it is shown here for the glossy 5 comparison with the rapid time series. So the idea here is that if you think that what can be the connection between the strength of AMOG and the Arctic, one common argument is that the freshwater export from the Arctic to the northern North Atlantic might be affecting it. I think we have kind of unexpected results that the lower resolutions have a lower export of volume and freshwater from the Arctic into the North Atlantic. The upper row is the volume time series from 3 configurations, and the lower results are the freshwater fluxes. AEROSI has the higher 1.4 volume transport out from the Arctic into the Labrador Sea, and a much higher 50% or more freshwater flux. At the same time, we're having stronger AMOG. So the connection between the freshwater flux and the AMOG is not necessarily that straightforward. We hope to further investigate this with the existing results. So here I'm showing the global upper ocean circulation, showing the speed distribution in the upper 100 meters as snapshots for September 2020, basically end of the G case GRA forcing, showing the 3 different configurations. The upper panel is showing the AEROSI, the lower left is the 60 to 10 highlight RASM, and the lower right is 60 to 30. So one thing you see that immediately with the 60 to 30, the lower right, is that the circulation in the higher latitudes, mid and higher latitudes, in the significantly underrepresented, especially in terms of the Kuroshio and the Gulf Stream extension. We have some improvement with the 6210 in the Gulf Stream extension, but Kuroshio is still relatively limited, and the Southern Ocean, being the low resolution in both cases, 6210 and 6230, it's underrepresented. When you go to a AEROSI simulation, you can see a much more active Kuroshio extension, and the Northern North Pacific, the Northern North Atlantic Gulf Stream, and a much more active Antarctic Circumpolar Current and the Southern High Latitude simulation circulation. When we go to the Arctic, in the upper half, the 100 meters for the March 2020, this is fully ice covered, mostly close to 100% ice concentration. So there's not much a strong circulation due to effect of the ice damping at the surface. But if you compare the AEROSI on the left, highlight RAS in the middle, and 60 to 30 on the right, you can see a stepwise improvement from the coarse resolution model to the high resolution model in the upper half, the 100 meters. When we go to the Atlantic layer, 250 meters to 400 meters, you can see much more differences, especially relative to the very coarse resolution, which is 30 kilometers in the Arctic on the right. The 60 to 10 kilometer and 3 kilometer in the Arctic look kind of similar, but I will show you another results in the next slide that dramatically quantify the differences. The circulation is dramatically improved in the higher northern latitudes, both in the 10 kilometer, especially 3 kilometer resolution compared to the 30 kilometers. So basically a take-home message is that if you care for the Arctic and connections of the Arctic to the global ocean and climate, you need to have resolution at least 10 kilometers or higher. If we look at the relative vorticity at depth of about 250 meters, that's a snapshot for September 2020. You can see that the AEROSI simulation is much more active in terms of relative vorticity compared to the 10 kilometer grid, and is definitely doing much better compared to the 30 kilometer grid. You can start seeing in the central Arctic mesoscale activity represented by relative vorticity. But if we go to analysis of Okubo-Wise parameter with the panel showing the northern hemisphere for September 1, 2019, from AEROSI simulation at the top and the highlight RASM simulation at the bottom. If you do look at the statistics based on the histograms, latitude versus number of eddies represented in AEROSI is going order of 1,000 relative to 120 in the 10 kilometer simulation, latitude versus frequency of eddies. And then if you look at the vertical distribution of those eddies, in the upper ocean, we have up to in excess of 8,000 eddies in the whole AEROSI simulation compared to order of maybe like 800. So order of magnitude more eddies in 3 kilometers in the AEROSI simulations compared to the highlight RASM 10 kilometer grid configuration. The sea ice is kind of tricky to compare. You can compare ice extent, but I don't like ice extent because it doesn't represent the actual full climate response in the Arctic. So time series of volume, sea ice volume are shown here from 4 different simulations. AEROSI on the upper left, the 30 kilometer V3 grid, it's on the lower right. Highlight RASM at 60 to 10 upper right, and the courses resolution 60 to 30 is in the lower right. Generally, what happens is that all those simulations, G cases with GRI forcing, overestimate the sea ice volume in winter. Sometimes, like in this case, 60 to 10, they underestimate the sea ice volume relative to kind of Pyoma's reanalysis with the University of Washington ice ocean reanalysis focused on the representation of the sea ice with sea ice data simulation. So this is not a perfect data set, but this is a proxy for sea ice volume for comparison. And you can see that 60 to 10 underrepresents in the early stages and then kind of get a better agreement in the later part of simulation. AEROSI starts with a better agreement in the early part and then eventually overestimates the later part of the simulation. We're still trying to understand this, and I think we have some ideas what's happening here in terms of tuning parameters for the thermodynamics and maybe even dynamical part of the E3SM AEROSI simulation, which we're still exploring as we go into loop 2 of the simulation. Equal grid 30 kilometer and the low resolution have the same kind of tendency overestimating sea ice volume relative to Pyomas. If we look at the spatial maps for ice thickness, and I'm showing here the 2 panels on the left, excuse me, from the passive microwave NSIDC data set for March 10, 2020 and September on the bottom. You can see that the spatial distribution is well represented in most of the models. The only difference is the thickness distribution. And I have a comparison to ISAT2, CRYSAT2 sea ice thickness distribution estimates for February, March combined 2020. So one thing you can see that they're probably all the simulations for March, E3SM, AEROSI, and other simulation configuration. Then overestimate the amount of ice drift into the buffer gyre compared to the estimates from the ISAT and CRYOSAT-2 for this particular time series. We think that the overestimation of ice drift is a real bias in most of the models, not just E3SM, but also CMIP6 and other simulations. And we're actively pursuing this idea in terms of trying to understand what might be causing it and how we can improve the representation of the ice drift and ice thickness distribution in the E3SM AEROSI simulation. So here I'm moving from the Pan-Arctic to basically understanding the gate weight exchanges. Apology for the background noise, but we have some construction going on in the building. So if you have a background noise, I cannot do anything about this. E3SM gateway transport across a Davis Strait on the left, Fram Strait in the middle, and the Barents Sea opening on the right. It's comparing the E3SM AEROSI at the top, 60 to 10 highlight RASM in the middle, and the 60 to 30 lowest resolution in the bottom. The main thing is that we're underestimating the amount of water flowing to the north through those gateways and the heat transport represented by temperature transport, which is the color shading in all the simulations. If you look at the Barents Sea in particular, Norway is on the left, south is on the left here in this case. One important thing that I would like to bring your attention is that the absence of the Norwegian coastal current next to the Norwegian coast, which is better represented in 60 to 10, the middle panel, and also AEROSI simulation, and also some recirculation within the Bear Island Trough out from the Barents Sea into the Norwegian and Greenland Sea, which is absent in the 60 to 10 simulation. This is important when we look at the total budgets. Now I'm showing the basically budgets for 4 gateways from 3 different cases, 60 to 30 in the upper left, 60 to 10 highlight RASM in the upper right, and AEROSI simulation at the bottom, compared to the known estimates from observations for 4 different gateways, Fram Strait, Barents Sea, Davis Strait, and Bering Sea. One important thing is that from observations, the problem is that we're not getting the net zero volume balance. So comparing the individual gateway transport to model estimates, it's challenging because we need to have a net zero volume transport from the model simulation to conserve volume and property. But there are some estimates of the ocean heat convergence into the subarctic region or Pan-Arctic region, estimated to be roughly about 124 to 160 terawatts. You can see that in the coarse resolution model, our net convergence, heat convergence is about 87, increases to 128 for the highlight RASM, and further increases slightly to 131 or so in the AEROSI simulation. The other interesting thing is that the coarse resolution model has a negative, so has the heat export from the Arctic through Fram Strait, which is definitely unrealistic. Might be related to the overestimated heat volume transport through Fram Strait being over 3 Sverdrup out from the Arctic. And most of the estimates for the Fram Strait are maybe somewhere about -2, -2.5. So AEROSI is getting it closer to observations. The other important thing is Davis Strait is underestimated. Davis Strait from observation ranges from about -2.6, which I believe is overestimation. More realistic, -1.6, -1.7. You can see that Davis Strait in the 60 to 30 and highlight RASM is clearly underestimated. We're getting it better with -1.4, and the same as I said for the high freshwater transport, which somehow might be interacting with the AMOC circulation in the North Atlantic. So one important thing why this heat convergence to the Arctic is important is that it basically couples to the atmosphere. The heat is released in the Nordic Seas and the Labrador Sea to the atmosphere via turbulent heat fluxes, as it's shown here as an example from the RASM simulation for March 1994. In the Barents Sea and the Nordic Seas, we have order of 150 to 200 watts per square meter in the monthly mean for a random month of March 1994. And you can see along the ice edge, which is represented here by the black contour lines, we can go up to excess of 400 watts per square meter in some location in a monthly mean sense. So communication of the turbulent heat fluxes to the atmosphere in terms of coupling and the effects of the atmospheric circulation is one very important aspect of AEROSI project objectives. Another one is heat convergence impact on the sea ice. There's estimates from the kind of like inverse models published by Tsubuchi et al. 2021, when they suggest that the current Arctic climate have an order of 170, 180 terawatt heat convergence across the 4 Arctic gateways, and the exchange over the Barents Sea removes order of 70 terawatts. So the Arctic receives about 100 terawatts of heat in the current climate state. This contrasts dramatically to at least 2 simulations that we found and performed. The highlight, CMIP6 high-res MIP contribution from CSM. They had a 151 contribution total with 69 terawatts converging into the central Arctic. And in this simulation, CSM had no ice in summer by the end of simulation. Similarly, with RASM, a fully coupled simulation for a total heat convergence of about 145 terawatts, and the net heat convergence into the central Arctic about 40 terawatts or so. We melt ice in summer in the central Arctic. So there's an issue with the observationally estimated magnitudes of the oceanic heat convergence, including the central Arctic heat convergence and the model simulations. And we think that with the AEROSI, we can address this particular issue. So finally, just before the conclusion, let's look at the heat convergence, turbulent surface turbulent heat fluxes from the 3 simulations. The AEROSI on the left, highlight RASM in the middle, and 60 to 30 in the upper right. You can see that AEROSI has a very strong turbulent heat fluxes both in the Nordic Sea, Barents Sea, but also the Labrador Sea for a snapshot in March 2020. Highlight RASM at 10 kilometers has the Nordic Sea and the Barents Sea possibly reasonably well represented, but clearly underestimate the Labrador Sea turbulent fluxes compared to AEROSI, and the low resolution, the core resolution, low resolution simulation underestimates in all the regions. So basically, to summarize, we believe that we have a very encouraging results from AEROSI simulations that represent improvements relative to the comparable core resolution E3SM simulations and whatever observational estimates that we have compared so far. Those simulations results provide encouragement for continued integration. We started cycle 2 of GRA 55.2, the driving ocean cycle, and we hope to complete at least 2 or 3 cycles. We'll continue with model optimization in terms of scale away physical parameterizations. We'll continue critical evaluation against observations, and we hope to address at least some process studies of the mesoscale processes in the Arctic Ocean. In the end, we hope to demonstrate by the end of this project that the coupling with high resolution atmosphere and land at E3SM configuration, the ice ocean model is ready for this type of configurations to advance DOE relevant science objectives. Thank you very much.